Our invited speaker for today's Laura Eslava from the Institute for Research in Applied Math and Systems, I think. That's the IIMS at the National University, Autonomous National University in Mexico. Laura did her PhD like
McGill University.
McGill, I don't know, but was it 2017, something like that? Yeah. Under the supervision of Luigi Alario Berri. Later, she did a postdoc at Georgia Tech. Now she's an associate professor at the IIMS. Yes, and she's gonna talk about the methods to cut random recursive trees, to destroy trees, but virtual trees, mathematical trees, not the real ones. Yeah. So please, the floor is yours.
Yeah, no actual trees were hurt during this talk. Yeah, well, thank you to the organizers for the invitation. It's a real honor to be presenting in this community. I really like it. It's very welcoming. And I want to thank all the audience for being here and letting me share with you the latest interest that I have on random recursive trees. And yeah, I may not have the longest name of the talk, but I do have the longest name of my institute. It's IMA-SUNAM, and yeah, it's all that. Okay, so let's go. So I want to give you a little bit of background on what random recursive trees are and why they would be kind of important, sort of, and what is with these coding trees in a nutshell. And later on, the motivation for coding trees, the twist that I want to give it is to have some sort of malicious coding in which we want to accelerate the process. And to accelerate the process, we want to make use of the knowledge that we have on high degree vertices and the structure they have in the tree. But well, that's kind of the main story that I want to tell you, like what are high degree vertices doing with these processes. But I want to focus the main part of the talk with the classical uniform coding process because it has a kind of very nice features. And then we will talk about malicious codings in one deterministic version and one random. So, okay. So you have heard about random recursive trees. Colin said something about generalizations on random recursive trees. You just keep adding vertices, and the way in which you select where the next vertex is to connect is uniformly at random. And this is very nice. We will be talking about the degree as the number of edges that are connected to this, say, vertex I. In this case, it is 2. And the height is the number of edges that you have to traverse to get to the initial vertex, which we call the root. And so in this case, the degree is directed and leaves have the degree 0. And two of the characteristics of recursive trees is that we can count them. It's very easy. It's if you have n vertices, the number of random recursive trees possible is n-1 factorial. And the fact that we are kind of sequentially adding the vertices means that if we take paths from the root downwards, then the labels are going to be increasing. Okay, so these are two important characteristics. And random recursive trees belongs to a wider class of tree growth processes in which we will fit the preferential attachment model. And we can have, for example, two parameters alpha and beta. And the parameter beta is kind of a homogenization of the connection probability. So every vertex has kind of a fair chance to be selected. But then when you have a parameter alpha being positive, that means that the more degree that you have, the more chances to be selected to be the next connection you have. And then actually, well, we kind of know the story of these random recursive trees. Random planar trees were first studied But when Albert and Barabasi came up with the preferential attachment models, they said this phrase, the rich get richer, and they actually exploded the conversation on random on this preferential attachment model. So it is another example of how not the initial birthed gets the credit, but somewhere along the process, some topic gets kind of super on point, and well, yeah. Okay, so the first case over here, it's a random recursive tree. And the one below, it's preferential attachment, kind of the classical version. And you can see how they are more or less the same, but preferential attachment is more compact because the degrees of the degree sequence is more concentrated around higher degrees. The spoiler is not so much of a spoiler, but I will talk about some persistence of hubs. Preferential attachment trees do have persistence of hubs. I will not be talking about preferential attachments. I want to focus on random recursive trees, which is kind of a downside because preferential attachment is associated with real world networks because of the characteristics on the degree sequence. And random recursive trees do not fit that scheme, but still I find it interesting, and I want to tell you more about maximum degree vertices. Okay, so before the structure of random recursive trees, in cutting processes, what we want to do is to remove edges one by one in order to isolate the root. So we will have our root now, they look like trees, like actual trees, and we will be deleting edges and focusing on the tree that remains connected to the root, because for some reason we want to get to this root. For example, if you have some fake news that you want to dismantle, maybe you can identify a person that is saying something incorrect, and then you can tell them, hey, this is not true, please stop spreading this bad news. And then that means that from some point on, this person is not going to keep spreading the fake news. But there is still the source of the fake news, and then maybe you want to kind of one by one keep saying, like, correcting things, right? Or the way the initial paper that talk about cutting processes frame it, it was like cleaning a river. Suppose there is a source of contamination in the river, then you can kind of implement some filtering devices in stretches of the river, and from then on the river is going to be clean, but there is still the source of the contamination to which you want to get to. And contrary to sequential cuttings, we have percolation, in which we could add a probability of removing the edges on a graph, say on a tree. And then when you, with a given probability independent for every of the edges, and in this case, what we want is to fragment the whole graph and to count how large the components, the connected components remains. So this is kind of a global thing in which you look at all the connected components and you want to know the sizes of those pieces. But in the sequential cutting, what you want is to actually get to the root by removing edges. Okay. Okay, so how do we do that? Well, in the classical version, the given distribution is just a uniform distribution, but I will present models in which the distribution may be different. And well, this is what happens. You select one edge and you remove it. You focus on the tree that is connected to the root. And from those set of vertices or edges, you remove the next edge. So once a connected component is removed from the connected component to the root, then you don't care about that piece of the tree. Okay, so far so good. The first model was phrased in terms of deleting edges, but actually you can also think about removing vertices. So if I'm going to be removing this edge over here, that means that would be equivalent to removing the vertex that is farthest from the root. Okay, there is a slight difference here, because if you are allowing to select vertices to be removed, then you might as well go directly to the root and remove it. So that's what I mean when I say, okay, we are not going to isolate the root, we might be even destroying the tree. Okay, but in general, for the asymptotic analysis of these processes, selecting edges or selecting roots is not that different, because, well, there is a chance 1/n that this happens. So yeah, we can think about like both cases being more or less equivalent. And there is this nice embedding in the continuous time. I won't be talking about it very kind of widely in this talk, but I find it nice. So how do you select uniform edges from the root? You just give a time. Wait a second. You just give a time to be cut for each of the edges, and then these blue cases are the first 3 edges that are going to be cut in the tree. Okay, so again, there are some clocks that are going to ring at some point in the connected components that have been removed from the tree, but you just don't listen to them. Like, you just keep counting the clocks that ring that are still connected to the root at any given time. Okay, so here's what I want to do. I want to find a way to speed up what is known. I will tell you what is known from the classical process. I want to speed up the process. I want to make the less connections possible, still isolating the root. And there is another approach that could be kind of resilient goal, in which you want to devise processes in which the root is going to resist until the end. And then, well, it depends on what side of something, of some fight you are. I don't know if you are for the trees or for destroying the trees. Okay, so this is going to be cutting processes, but for telling the story of cutting processes, I want to tell you what characteristics of recursive trees we want to exploit. So the degree sequence is just taking any given integer k and count how many vertices have degree k in that vertex, in that tree, when the tree has n vertices. And what is known is that the proportion of vertices that have degree k decreases geometrically with k. And this is kind of the main downside to relate random recursive trees to real world networks, because real world networks decay not geometrically, but with a power law. And well, this result, well, the first result about this was in the 70s, and then there is a bunch of incremental results about this degree sequence, and then Svante Jensen came with a polya-orn system of that allows us to take care of the whole degree sequence, well, with finite dimensional distributions, but still you can phrase it in terms of the whole sequence. And well, look here, determine that the maximum degree has logarithmic order, and there is some well, after you place the maximum degree in this logarithmic order, the fluctuations are going to be Gumbel. And Gumbel distributions are associated to the maximum of, say, independent normal distributions. And for my PhD, we gave more details on the fluctuations of, say, this Gumbel distribution. And what is interesting about this is that one can study the degree of the root. The degree of the root is just a sum of Bernoulli variables in which you ask all the rest of the vertices whether you connect to the root or not. And then this is a Bernoulli random variable with parameter 1/i for every vertex, I minus 1 for every vertex I. So the expected value of the root the expected value of the degree of the root is going to be log n, natural logarithm n. But actually, the maximum degree it's log base 2 of n, which is larger. That means that although the root has more chances to have higher degree because it is the one that has been the longest, the maximum degree is not the root, which I find it fascinating. So what happens with vertices with the largest degrees? You can order them, and then well, there might be some ties. It's not that all vertices will have different degrees. And we can describe the height of the vertices with maximum degree like this. They are asymptotically independent heights. Well, okay, let me explain. This result is part of my PhD project, and later Bas Lodewijk was able to give the labels of the of these maximum degree vertices. Okay, and well, kind of it's well shaped. And there are two things that I want to highlight here. If you compare with the insertion depth, if the next new vertex that you attach to a random recursive tree has logarithmic height, but it has say a different constant in the logarithmic height and a different type of concentration. But what happens when the height of a given vertex is logarithmic of logarithmic order? That means that you are not talking about the same vertex, because when you add a new vertex, this vertex, the distance to the root will never change ever again. So if we are describing the depths of vertices with high degree, if we are describing vertices with with the highest degrees, their height in terms of asymptotic expansion with renormalization, that means that those highest degree vertices keep changing. And that's what I refer to non-persistency Hopfs. So in comparison, when you have preferential attachment models, after a while, there are going to be vertices that have so much degree that from the rest of the time on ever, they will keep accumulating the most of the degrees. So you will run the process of preferential attachment model, and at some point you will be able to say, okay, these are the 5 winners of the game. And that's it. They keep accumulating degrees. But in the random recursive trees, this is not true. There is kind of a race of being lucky and being old enough. And I think that's a nice way to see life, because it's not all about preferential attachment.
Is alpha there? What's this alpha there? Is not...
It's kind of 1 minus log of 2. Like it's known.
No relation to the alpha that you...
No. No, it's not related. Like all alphas are not related in this talk. Sorry. Okay, so this is why random recursive trees fascinate me. And now we want to, well, at the end of the talk, I want to relate all the knowledge on these high degree vertices with my cutting processes. But I guess it's time to tell you about uniform cutting processes. So this is beautiful. You will see. Well, this is not so beautiful. Okay, so now let's think of our xn to be the numbers of cuts needed to isolate the root. And how are you going to select edges uniformly at random from the tree that it's there? And then the first thing that you can ask for is to know what's the growth of the expectation. And the growth of the expectation is of order n over log n. Okay, so it's actually that you have to cut most of the tree, like it's order n, but by log n. You don't really care about the log n. And then there was some analytic combinatorics involved to prove this asymptotic convergence to a Cauchy random variable. And then there was a probabilistic point of view on how to prove this convergence. And I want to talk about the probabilistic view. Well, it was nice because the probabilistic view can be exploited to relate it to coalescent processes. And the Bolhausen-Sneedman process was identified by Christina Goldschmidt and James Martin in 2005. And this is nice because this process is related to viruses. Viruses reproduce differently than other species because it's kind of the genealogies kind of exploit. Well, I should ask me in coffee break about the Bolhausen-Sneedman coalescent. And then for the coding processes, you can isolate other vertices. So you wanted to isolate the root, but maybe you want to isolate for some reason one of the leaves or two leaves at the same time, and so on. So there were many generalizations about that. And all these generalizations were kind of top up with a structure that is called the code tree. And this code tree, it's kind of encoding. It's kind of in the middle of sequential coding and percolation. It's an encoding of what happens if you keep destroying both trees. You start with a tree, you remove an edge, now you have two trees, and now you want to destroy both trees. And now the next edge that you remove, you want to destroy the whole graph. And the code tree, wait a second. The code tree encapsulates all that information, and then you can read off whatever previous results you want from there. And this code tree works very well for Vietnamese Galton-Watson trees. So there is a bunch of literature on that side too, because Galton-Watson trees have this property of whenever your kids are born, they behave independently. So you can take advantage of those properties to work with Vietnamese Galton-Watson trees. And then the code tree, the limiting process of the limiting tree of the code tree corresponds to continuum random trees. So everything kind of works nicely. Okay, so let me talk more about this splitting property that I was telling you. Okay, so the splitting property means that you will have these distributional equations, which means that if you want to count the number of edges being cut at a given time, you want to count the number of edges cut to remove the tree. Well, you take one first cut, and then you look at the size of the remaining tree, and then you have to do the process all over again on that smaller tree. But that distributional equation relies on the remaining tree having the right distribution. That's it, like it's a random recursive tree. If it were to happen that the remaining tree is not recursive, then you wouldn't have this nice distributional equation. And this is kind of one of the bases of most of the results that one obtains with cutting processes. Okay, and I forgot to put a reference here, but Jansson framed the counting of this number of cuts in terms of records. Okay, so now records are nice to work with because, well, this is kind of a branch. Well, if you just focus on a path and you want to know how many cuts you have to make until you get to delete the initial edge, then you just have to count the records because first you cut just along this branch. First you cut the last one, then you cut this 1.15, and you don't care when this edge rings because that is going to be removed from the main structure by the time it wants to be cut, and so on. So well, there is this branching structure that has to be dealt with, but actually this framing of records allows for some analysis on these cutting processes. So do you like this record structure? Okay, so that means that you like if you want to know whether an edge is going to be removed or not and chip into the number of cuts xn. You just need to look at whatever edges you would be crossing to get to the root. If you are a record in that way, in that path, then you will be one of the edges that you need to remove to isolate the root. Okay, this is important. Look at it. So now let me tell you about, before continuing with the uniform cutting process, let me tell you about our first attempt to being a malicious person. So if you want to get the fastest to the root, maybe you should go for the vertices that have highest degrees, right? Because at least you are removing a lot more children, and perhaps with them you are removing a lot more vertices from their subtrees. And if you were going to be kind of an almighty person, maybe you know the ordering of these vertices, and then you keep removing them from the vertex with highest degree to the second highest, and so on. And then, well, this should be faster. And it actually is faster, because the number of cuts in this process needed is going to be a sub-polynomial. Okay, so it's n to some power, but the power is not 1. Okay, so this is good news, except that this is not kind of applicable, because we wouldn't, like, finding this ordering is kind of hard, right? Like we don't really know. And it's also an overcount, because we will be skipping vertices. Like if you have 2 vertices that are a very high degree, and one is on top of the other, one is an ancestor of the other, then you won't be having to remove both of them. So you are kind of, in this process, you are saving some steps. This means that the number of cuts that you do in this process until you isolate the root is, well, in principle, if you are, the worst case scenario is that you will have to delete all vertices that have degree larger than the root. But this is an overcount. But in any case, we were exploiting the results I have from my PhD. We can say something about this random variable. So far, so good. And well, there are downsides to this process, because this process is not going to have the splitting property. So knowing that the vertex that you are deleting has high degree means that you are asking a lot of the tree that remains. You have information about the tree. So now the tree that remains is not going to be a random recursive tree. There is no splitting property. And we also don't know what is the size of the subtree that you removed. So we are kind of stuck in that process. But we wanted to know how far away we are. Okay, so the colors do not correspond. Sorry about that. I am sometimes dyslexic with colors. But by simulations, we estimated how large was this actual variable. And we use this record counting, but just with degrees. Okay, so how do you know that you are going to be cutting a vertex towards trying to isolate the root? It's because it's going from the root down to this vertex, say, of degree 3. No vertex before has degree larger than 3. So for sure, you are going to be cutting this vertex. So that is easy to implement. You go around you go around the tree and ask every vertex, are you a record degree wise? And if they say yes, then you count them. So that is what allows us to make these computations. And we discovered that, well, what was not a surprise, that our estimation is not, our estimation of counting all vertices that have larger degree larger than the root is not enough. So it's an open question to understand more about the structure of these vertices with high degree. If you select a vertex and you discover that it has high degree, how many of them below are also kind of these high degree vertices. Yeah, then like you will have like n to the alpha, some other constant alpha. You will have like n to the alpha high degree vertices. So these are actually quite a lot. You expect to be having some descendants of degree larger than the root if you already are large degree. Okay, so that's it for the detour with the record counting and the degree records counting. I want to tell you about the probabilistic approach of the uniform cutting. So I just say to you, and I wanted you to believe me, that there is this splitting property, which means that once I cut an edge, both trees over here are going to have a random recursive distribution. So I won't be arguing that, but I want to count how many edges, how many vertices are lost with the first cut, so that I know how much I have reduced my tree. So say I know I will be removing k vertices. Okay, so let's compute what is the probability of removing k vertices. Okay, so this is going to be like favorable cases over total amount of cases. And the total amount of cases is, well, there are n-1 factorial number of recursive trees. And I have to select one edge. I have n-1 edges. So far, so good. If I want to remove k vertices, I have to select the labels of these k vertices and the hook in the terms of calling terminology. I will be connecting this edge, this vertex with an edge to the main tree. So I need to select k+1 labels. And once I select the k+1 labels, this vertex is determined because it has to be the one with the smallest label, so that it gives the characteristic of being an increasing tree. And then how do you arrange the rest of the labels? Well, just as a recursive tree. And this is kind of the property that I'm not kind of justifying today, but we just plug in kind of the number of ways in which you can assemble the labels in an increasing way, which is kind of the only restriction that we had. And then when you simplify all those terms, it's a very nice formula. You have almost 1 times 1 over k plus k+1. And then you can see that this is almost like a heavy tail distribution, and there is an idealized random variable of this form that takes values in all natural numbers, and it's perfect. This is why mathematics is so lovely, because it turns out that my mascot is actually the same distribution as this idealized random variable, conditional on having the right cut. Okay, so say you have this idealized random variable that can give you any number in the naturals you want, but if it gives you a number that is larger than the size of the tree, well, this doesn't correspond to a mass loss. But conditional on this C being at least reasonable size, then it has the distribution of the mass loss, which is perfect, because now we don't depend on n. We have a random variable that we can add, and we have a random walk with a barrier in which we will be kind of accumulating the mass loss, all the vertices that are removed from the trees. I am accumulating in this random walk, and whenever I try to cut more than I have in my tree, I say, okay, skip this step. This is kind of an accept and rejection argument. Skip that step. This doesn't correspond to my model, but keep going. And then at some point you will be left with one vertex, in which case you cannot keep going with the walk, and you can count the number of jumps that this random walk has. And this is the number of cuts of your process. Okay, but there was no improvement in that. The real improvement, the real good idea is that we can remove this conditioning on not surpassing the barrier on n, and just ask how many steps do I have to take until I go above n? And this means what many steps do I have to take before my coupling of these two processes becomes different, right? Like the first time I attempt to do a cut that didn't exist, my coupling is not longer real. I stop then, and it turns out that the two processes are going to be asymptotically the same, because when you have when you encounter a step that was too long, and you don't do that, the size of the tree is already small enough that the remaining steps, even if you remove leaf by leaf, those steps, those number of remaining steps is going to be negligible compared with the size of n. So this is the probabilistic view. I really like probabilistic arguments, and this is very nice. So we really wanted to make it malicious process. So we really wanted to accelerate the process and to have something something going on with high degree vertices. And our first attempt was deterministic. We have a random tree, but we pretend we can order the vertices from highest degree to lowest. And deterministically with that sequence, we remove vertices one by one. So now we want to make it random. How do we make it random? We do it degree biased. So now instead of having a deterministic sequence to remove the vertices, I will say I will remove a vertex, but just biased toward vertices that have higher degree. Okay, so you expect to be removing high degree vertices. Well, maybe not, but that's kind of, okay, pushing towards vertices with highest degree. And actually, that is going to be the same in distribution as selecting uniform random edges, but instead of cutting the far point, you cut the one closest to the root. Okay, so you know how an edge is always associated in a rooted tree. An edge is always associated to a vertex that is not the root, because you go for the farthest vertex. But actually, if you select an edge and you go for the closest vertex, then that vertex is going to be size biased by the number of edges that have as children, right? So it has a nice equivalence. And once we are selecting edges uniformly at random, then we can do the same counting process for the mass loss, and actually the splitting properties maintain. And I want to show you the mass loss distribution. This is the last computation I will be doing. Don't worry. And then there is going to be a problem that because now we are facing things in terms of deleting vertices, there's a chance of actually selecting an edge that is connected to the root, and then it's instant destruction. Okay. And I might not have time to tell you why this is important, but like with pictures, but I will say a little bit about that. Okay, so if we will have the splitting property again. So to count the number of vertices deleted until destruction, you take one vertex out, and then you keep going with the same process, but with a smaller tree. Okay. So again, let's pretend we will be removing k vertices. So I have to, this is the denominator of the computation we did before. So I have to select the k plus 1 labels of my removed vertex plus the hook. And I would have to count, this is strange. I will have to count all the ways I can arrange the main subtree. And before I was counting all the possible ways to arrange the labels in the tree that I will be removing. But because now the way to get to this precise way of cutting the tree depends on how many edges my root has, this is not the right computation. I have to go over all possible subtrees with k vertices and count the degree of the root, right? Because to precisely remove this vertex over here, I have two options of selecting the edge that I will be removing. Well, the edge that will be pointing to the vertex that I am removing. So I have a parameter that depends on the tree that I will be drawing here. Well, we take expectations. If we take expectations, I recover the same factors that I had before, and I have the expectation of a random recursive tree, which I was telling you is just logarithmic size. It's a harmonic number. So actually, we recover the same expression, just with an extra harmonic number. Very precise, everything happens. And then I forgot to say, this is joint work with Sergio Lopez and Marco Lopez in Mexico City. Marco is a PhD student, and it was his project, his thesis project. And then when we got to this point, he said, "Oh yeah, so let's go for it." And actually, if you blinded, like being blind, you just put this probability as a distribution on the natural numbers, you do get a probability distribution. So this is kind of nice. Mathematics again do their job, their beauty. But then there is a problem. It's not actually working to have the right correspondence. So now we have this idealized random variable psi hat, but this conditional on having the right number of vertices to be removed is still not corresponding to our actual random variable. But on the good side, it is stochastic domination. There is an stochastic domination, which means that our idealized jumps are smaller. And the reason why they are smaller is because there is a heavy atom on instantly destroying the root. So now the root has this logarithmic degree. And now the probability of selecting selecting the root is not as innocent as it was with the first process. So this is what is coming into our problems, and that means that, well, we can come up with a random variable that is larger. If I'm making smaller cuts, then it would take me longer to cut the tree. And well, just with the strategy of the random walks with the barrier, we can get asymptotics for the fake number mn. So this is kind of sad because, well, it's nice results, nice asymptotic results, but just for the fake random variable. So yeah, so now what is open here, and I didn't put it on the slides, is how did you make this process a little bit more faithful to the real model? So maybe these random walks that corresponds, well, the random walk approach of X and of unmol, maybe you can kind of have a random variable that just stops it at some point and say, this is when this instant destruction happens. But well, I don't know, like, if you have any ideas, tell me. And just to change a little bit, do you have any questions? Sorry. Okay, just like a side note, there is this other way of generalizing these coding processes, and this is kind of more positive. This aims at resilience. And now with this resilience, we want to slow down the process. So how do you slow down the process? You say that whenever you cut an edge, the edge resists k cuts before being deleted. So before deleting an edge, you have to try k times to remove it. And this is going to slow the process. And the computations that have been made are are on their early stages, and they get the expectation. The expectation changes. Remember, it was n over log n. So now you have even a smaller order of logarithmic factor. So so what I want to do next with min-1 is to go for this probabilistic approach in which we will have the mass loss, the continuous time embedding with these exponentials. But now if you have to cut k times, then you have to wait until k exponentials rings, which is a gamma distribution. But maybe with a time change, we can pretend those gammas were not gammas, but exponentials, and keep going with the analysis. Hopefully we will get something. And yeah, so as a summary, we have a classic model of cuts in which everything is known already, like the expectation has order n over log n, and we know how to take out deterministic values to get to the random order. And if you want to make malicious processes in which you want to speed up the process of isolation, then there is a way in which you can really destroy it, like change the rate of, change the speed, which is by knowing which are the vertices with maximum degree, except that we don't really understand vertices, the substructure of vertices with maximum degrees. If you go for a random process of selecting the edges, actually you don't gain that much, right? Because with the classical cuts, you take n over log n times, and with this degree bias that was supposed to be super nice, pointing towards vertices with high degree, you only gain half the time. So you are actually kind of targeting the vertices with highest degree, but it's still kind of no real gain. And there is still something to know because, well, this was kind of the approximation, like the upper bound. Maybe we can gain something with the instant destruction part that we are missing. And on the classic cuts, okay, so with these random approaches, we always will have like order expectations of n over some logarithmic terms. So it's kind of weird. Yeah, that's it.